These notes are intended especially to help you understand the idea of torque as a cross product, and a cross product produces a vector as an answer or result, and how can torque be a vector when it has to do with rotation? In fact, all the rotational quantities can be and usually are expressed as vectors in higher level physics. So that's what we're going to answer. How can rotational quantities be described using vectors? How is that even possible? A vector just like points in one direction like that, whereas rotation involves this kind of motion. It doesn't seem to have anything to do at all with an arrow. Well, it's a purely mathematical construct. It's a tool. So let's do a quick recap of vectors. They're a math tool like numbers. For example, if we had never invented numbers, if we wanted to say we have this many of something, we might have to draw it like that or go like this. Okay? In fact, if we didn't, even this is an abstract concept, we'd have to draw the original thing. The first thing that happens with human beings, if we want to say 4 people, they have to actually draw 4 people. And then they graduate to just representing people with like dashes, and then finally an actual symbol that means our concept of 4. That's an invented symbol, an invented concept. Well, vectors are the same thing. They're a math tool that was invented to describe things that are like numbers because they have amount, but also include the idea of direction. Our tool is just an arrow. And the arrow has a length, which represents amount or magnitude. And what's the other thing that all arrows have, all vectors have? Of course, it's direction. So direction is the thing that's added to the concept of number. It has number or amount and direction. All right, so now let's look at rotational quantities and watch what comes out of this. Here's a disk, and of course it can spin with a small speed or a higher speed, and it can spin counterclockwise or clockwise. So those are the possibilities of the concept of spin. So we represent that with the symbol omega. It means spin speed, and what's the other thing that this omega tells us if it's got an arrow over it? It means spin speed and direction. That's what that symbol means. So here's a small speed counterclockwise, there's a larger speed counterclockwise, and there's a speed clockwise. So this covers the kind of different things. The speed can be small or big, and it can be clockwise or counterclockwise. All right, alpha is the change in omega per second. So here's some examples using the idea of direction. Here's an omega, which is counterclockwise, right? Counterclockwise. This omega is counterclockwise, and this omega is clockwise. And now let's look at the alphas. This alpha is counterclockwise, this alpha is clockwise, and this alpha is counterclockwise. Then ask yourself, what would happen to the omega in each case? Here the alpha helps the omega get bigger. It's the meaning that the change in omega is in this direction. Every second you're getting more omega this way, so omega increases. In this one, omega would decrease. I think that's obvious, so I'll go a little faster. And then this one, omega would decrease. We could represent these two directions, counterclockwise and clockwise, with signs, positive and negative signs. This would be a positive omega, this would be a positive omega, and this would be a negative omega. Same thing with alpha. This would be a positive alpha, this would be a negative alpha, and this would be a positive alpha. Okay, all of this we did with translational velocity and acceleration, the same idea, but look at what we're getting towards. We're getting to that idea of direction, which could be represented with a sign, positive or negative, and something getting bigger or smaller, in other words, a change in the amount. We can do the same thing with torque, right? This one force around that axis will create a counterclockwise torque. This creates a clockwise torque. And this is a bigger force, so I've drawn the tau bigger. This creates a bigger counterclockwise torque than this one does. So notice we've still got the same idea of amount, right? Small torque, bigger torque, and direction, counterclockwise and clockwise. Amount and direction, or magnitude and direction, in these real things that happen. Okay, if it's got magnitude and direction, we can represent it with a vector, because that's what vectors have. All right, so to describe these things with a vector, like means omega, alpha, and tau, the length of the vector will show, guess what? It will show the magnitude or amount of the omega or alpha or tau. So we're going to write duh here, because that's the easy part. But how does a vector which points in a single direction in space represent counterclockwise or clockwise? And in fact, even counterclockwise and clockwise wouldn't really be sufficient, because let's say we have this thing spinning like this, and this one here is also going to spin what would technically be clockwise, but we're going to turn it at an angle like that. So they're both spinning clockwise if you look at them from the correct way, but they're definitely not spinning the same. This is spinning in this flat plane, and this is spinning in a tilted plane. So we need a way to say that those two things, even though from one point of view they're both spinning clockwise, that they are indeed spinning in different ways. Okay, so we need a way to represent direction using an arrow, using a vector. How do we represent the direction something spins using an arrow? Okay, and this could be called right-hand rule number 2. You already learned right-hand rule number 1 for torque. This could be called right-hand rule number 2. And it's easier than the first one. It's fairly straightforward. You look at the spinning. You kind of cup your hands like this. It's got to be your right hand. Cup your hands like this so that the axis goes through the middle, the gap here in your hands like that. Then you point your fingers in the direction of the spin. So see, I've drawn in omega. So I point my fingers, I've got the axis going through like so I could hold this pen. And you make sure your fingers point and curl in the direction of the spinning motion like that. Here it's counterclockwise. Then you make your thumb, if you were holding your thumb like this, you have to change that, make your thumb perpendicular to the plane of the spinning. So it'd be like that. So this kind of spin will be represented with a vector pointing up, away, and normal to the plane like that. We could represent that by a dot, like the point or head of an arrow. Then you do the same thing for this one. You look where the axis is, you cup your hands around it like that. Then you make your fingers go in the direction of the spin. Uh-oh, so these are going the wrong way. So what do you have to do? You have to turn your hand upside down, like that. So it's still, the axis goes through the gap in your hand, okay? But now your fingers point correctly in the direction of omega, in the direction of the rotation, and then you make your thumb perpendicular to the plane, and now your thumb will point down into the page, and we represent that with an X, which is like watching the trailing feathers of an arrow that's pointed away from you. That's right-hand rule number 2. It's much easier than the other right-hand rule. Make sure you do it with your right hand. Once we've defined these rotational quantities that way as vectors, as arrows, everything works. Nature is fortunate for us in this way that all the concepts we had from before still work as long as we define rotation as arrows. So when we write this familiar equation of motion, we can write this as a vector equation and think of this omega as, this omega here is the initial omega as an arrow, and then this alpha is an arrow, and then the result is the sum of those two arrows. And everything works. Like the arrows are either going to point like up at you for counterclockwise and down for clockwise, and you add them just like you add arrows. All the rules for vector addition work. Everything works if we define our vectors that way.